All right, guys. So welcome back to another video about forces in AP Physics C mechanics. I'm gonna be honest, this is kind of a big mix of things in this video. You can see the names of all of the different topics that we're covering. Section 2.2 in College Board's course and exam description is free body diagrams, which, it's a lot of us have done free body diagrams before back in AP Physics 1, so I don't think we need to spend as much time or have a full video just about that, when really we're going to be using free body diagrams in conjunction with other topics for this entire unit. Likewise with Newton's laws, he's got three laws of motion. We've probably seen or at least heard about all of them before, so we'll talk a little bit about those, review them. And mainly kind of just touch on or review the different types of forces that we have. In the next video, I actually do want to go through some different examples, and I'll actually probably break down each of these different types of forces into some different videos. Section 2.6, for example, is all about gravitational forces. 2.7 is all about springs, or no, friction. 2.7 is friction. Section 2.8 is about springs. 2.9 is about resistive forces, so things like air resistance. And then 2.10 is about circular motion. So, circular motion, gravitation, I think I'll probably kind of lump together. So kind of go a little bit out of order from what College Board suggests. Because I do kind of think that a lot of this stuff goes well together. It's really hard to separate it all into just one video. So, one video per topic, that is. So, all right, but without further ado, I really just kind of in this video want to touch on a couple of things. First off, what is a free body diagram? What does it do? Why do we draw them? Things like that overall too. How should you draw them is the most important thing I think we'll probably talk about. And really what these free body diagrams are, you probably all know, they're used to visualize the forces that are acting on something, right? These forces are all pushes and pulls caused by something or someone in order to get an object to change how it's moving, whether that's to speed it up, slow it down, change its direction, or just simply keep it moving at a constant speed. Forces are a very vital part, not just to the curriculum for Physics C, but also to our lives, right? And free body diagrams are essentially just things that show you all of the different forces acting on something. So you can imagine that you're like maybe above the ground and you're looking down at the ground and there's like a car that's stuck in mud or something. Or maybe you see three friends fighting over a box of pizza or something. Well, one friend might be pulling that box of pizza up and to the left. Another one might be pulling that box of pizza downwards from your point of view. And another one might be pulling it to the right. And all three of these arrows show us different forces. But then you might have a fourth friend in the mix who's supporting that last friend, right? Maybe a fourth friend is also going to pull that box of pizza to the right. Well, now what you're seeing, not quite sure why it erased there, but now what you're seeing is that there are two forces to the right. So most importantly, right, free body diagrams, again, they show you the forces that are acting on something. They always start on the dot that's provided to you. They're always pointed in the direction the forces are applied. They're never split up into just horizontal or just vertical in the case of a diagonal force. So you'll notice that I've drawn that diagonal force, well, diagonally. That splitting up to horizontal vertical is something you do when you're solving the mathematical equations to go along with this. And then, of course, the actual length of the arrows are used to actually indicate what type of force there is. Not to mention, you also have to label these diagrams. So say, if all four friends tied ropes to this box of pizza, I feel like this pizza is just going to hit the ground at this point. It's going to fall out of the box or something. But all four of these would be labeled tension force. And I typically like to label them F with a subscript of T for tension. And then you have to put the arrow above them to indicate that they are forces. So in Physics C, there's a wide range of forces that we actually talk about, two of which are saved for electricity and magnetism. So I'm not going to mention those here. But you've got things like gravitational force or weight, right? Gravitational force and weight force are the same thing in terms of our free body diagrams. Those you can typically notate F subscript of G is the most common one. You can also use F subscript of W, or you can use W. What you cannot do for gravitational force is you cannot just use the letter G because that's used for acceleration. Or if you use uppercase G, that's reserved for the physical constant. So it has to be or should be one of these three things. Either these are the three most common ones to see: force due to gravity, force due to weight, or just simply weight for your labels. You also have, like we talked about, tension. You could label that in a couple of different ways, either FT or just T. Right. And I guess I should also maybe talk about where all what causes all of these forces, and what direction they're going to be pointing. Right. Gravitational force is caused by the Earth, and it always points to the center of the Earth. Always points to the center of the Earth. And there's actually two equations that we could have for gravitational force. One of them, which is used when you're close to the surface of the Earth, because then the acceleration due to gravity is approximately constant, is that you can just say that the gravitational force is your mass of your object multiplied by what we call the gravitational field or acceleration due to gravity. That's that 9.8 or 10 meters per second squared that we're so familiar with. The second possibility, and this is typically used more for things that are not near the surface of the Earth, so something changing its distance from the surface substantially, or on a planetary scale, is you would have to take the fundamental constant g on your equation sheet, multiply it by both masses involved in the gravitational force, and divide it by the distance squared between their centers. So that those are the two equations that we have for gravitational force. You usually use the first one, but the second one is used when you're talking about things more so on a planetary scale. Tension, of course, is always caused by a rope pulling on an object. And what you'll see is that all of the rest of the forces, right, aside from gravity, all do require direct physical contact or as close to it as we can get. So that always is pointed in the direction that the rope is pulling your object. You've got normal force, which is the force normal or perpendicular to a surface. So it's caused by two surfaces pressing together, and it always points away from it points away from the surface causing it. So if I were to say that I have like a box on a ramp or something, well, then the ramp would exert a normal force on the box, and that normal force, which could either be N or F subscript of N, would be pointed directly away from that surface. Notice how it's normal or perpendicular, to that surface, or at least it would be if I'd drawn it a little bit better. So, you've also got spring force caused by springs stretching or compressing. That's also on your equation sheet. We say that the spring force is given by negative K, which is a spring constant, how stiff your spring is, multiplied by the displacement of that spring from its equilibrium or its natural length. So regardless of whether you press or compress a spring, you will have a spring force trying to restore it back to its original length. The other types you've got, let's see, you've got friction. You've got two types of friction. Static friction is when there's no sliding between your two objects, and kinetic friction is when there is. And whenever two surfaces are trying to rub together, that's where friction is important. And the equation sheet has it written like this: F friction is less than or equal to the coefficient of friction multiplied by your normal force. Note that static friction follows that trend, whereas kinetic friction is always going to be equal to its respective coefficient multiplied by the normal force. So static friction can be less than the coefficient times normal force. because its only purpose is to prevent your two objects from sliding against each other. And we'll see then some examples. Kinetic friction always has to be equal. The other types that you've got are, I guess really the only other type that we typically talk about is drag or resistive force. So drag and resistive forces are caused by things like the air. You can basically always ignore these unless the problem says otherwise. College Board themselves has said that you can ignore drag forces unless otherwise stated. And typically, when you have to work with drag or resistive forces, it's given by negative some constant multiplied by the velocity. So if you're like a tennis ball falling through air or a sheet of paper falling through air, then the faster that you fall, the more air resistance you're actually going to experience. And then that B value just kind of tells you how strong that resistive force is. It's different for every material. You don't typically have to worry too much about that B value aside from just it tells you strength of resistive force. All of those put together then allow us to solve and come up with equations for an object's motion, its acceleration, velocity, or position. All of that is accomplished by using Newton's second law in conjunction with some of his others. So this is his second law. It's on your equation sheet. Acceleration is net force over mass, right? The first law just simply says that if mass is zero, then if the net force is zero, then the acceleration is zero. And it says that anything with mass will oppose a change in motion as well. The bigger the mass is, the more resistant it'll be to changing its motion, or the more resistant an object will be to accelerating. And then finally, the third law says that every force in the universe has an equal opposite force. And that not only, but it mostly matters when you're dealing with two objects in a scenario. And you're typically asked about how the two forces will compare. Well, if they're the same type of force, they're two different objects, they're equal in magnitude and opposite in direction, right? Because of Newton's third law. So I exert as much gravitational force on the Earth as the Earth exerts on me. And then how you use all of this with circular motion, which is section 210. And again, we're going to take a look at a lot of examples with these because, forces is a lot of examples. But you can say that the acceleration of something in circular motion is going to be, if it's in constant speed, that is, then it's going to be directed towards the center of the circle and given by this formula, the speed squared of your object divided by the radius. If you have a non-constant speed, so if you're either speeding up or slowing down, then you're going to have a centripetal acceleration, but you're also going to have an acceleration tangential to the actual circle that your object is moving on. And if you do vector addition, then those will actually give you the total acceleration. Typically, you don't have to worry too much about that mathematically. But again, if your object is either speeding up or slowing down, then you have two components to your acceleration. That extra part tangential to the surface, to the circle, that is going to be important. Again, we'll take a look at all of this stuff in a next video when we take a look at some examples, but just kind of a quick rundown of most of the formulas, the different notation that we're going to be using. Next video, I think we'll kind of focus a little bit more on things like tension, pulley problems, some friction. After that, we can take a look at some spring stuff. We'll do a separate video for resistive forces because that is a little bit longer of a topic. And then finally, we can talk a little bit more about circular motion and gravity. So thanks for watching, guys, and I'll see you guys in the next video.